Loud and clear.
Can hear you also.
Okay, beautiful. Right. So in today's session, just so all of us are aware, I've already started recording, right? So just make sure your mics are off. Only turn them on if you want to say something, right? But just make sure they are not on by mistake, right? Right. So today we are going to go through bearings, right? On Sunday we had a session. The session was on the first unit on gear drives, right? I found it important that we first go through that portion of gear drives before we do bearings, right? Because gear drives essentially is a prerequisite for bearings, right? So today we're going to look at bearings as they will be part of your second assessment, right? So in your second assessment, you'll have modules 4, 7, 5, and 8. Right, so there is precision measurement, hydraulics. What is this? So after hydraulics, uh, module 5 is gear drives. Yes, so gear drives or a portion of gear drives, as well as bearings. Right. So we've already gone through the other modules. Now we will go through bearings. Right. Now I've shared my screen with you guys, so I just need you to confirm if you see my screen here.
Yes, sir, we can see your screen.
Okay. Right. Let me just go to these notes. Right. Bearings. Mm, mm. Okay. Can everyone see this?
Yes, sir.
Okay. Right. So bearings is module 8 on your textbooks. Right. Now I am using the white and yellow textbook by I think R. Cameron. I think it's by R. Cameron. Right. So if you're using that textbook, you should have right the pages I'm going to be referencing from. I don't know what's going on here. Just give me a moment. Okay. Right. Okay. So we can continue now. Right. So we are doing module 8 bearings. Right. Now under bearings, essentially this is what we will be looking at. Right. Bearings we are able to use as essentially supports. Right. If you can think of if you have a shaft and the shaft is fitted with bearings, right? The shaft itself we are able to take as a beam, and the bearings we are able to take as supports, right? Now, typically, this is the kind of scenario we'll be looking at, right? Where you have a shaft, right, and then on the shaft they fit a gear wheel. Right now, as far as gear wheels and pinions, that we covered on Sunday when we looked at gear drives. Right. So by now, I would assume you understand what I mean by when I say a gear wheel. Right. Now, typically for bearings, this would be the scenario. Right. You would have a shaft, and the shaft would be fitted with a gear wheel. Right. And then sometimes it is also fitted with a belt drive system. Right. Now, when it is fitted with a gear wheel, or if it is subjected to any kind of load, right? That is why we need bearings, right? Now, the bearings, as I mentioned, act as essentially supports for the shaft, right? Depending on the kind of loads that the shaft is being subjected to, right? Now, regarding the loads that the shaft can be subjected to, right? We get loads that are essentially perpendicular to the line of action of the shaft, and then we get loads that are parallel to the line of action of the shaft. Right, so the line of action is essentially the center of rotation of the shaft, essentially the center line of the shaft. Right, so when I say the line of action, I'm referring to the center line of the shaft. Right, so the shaft is subjected to, or can be subjected to, loads that are perpendicular to the line of action and loads that are parallel to the line of action. Right, now we get different types of bearings. Right, bearings that support different types of loads. Right, we get bearings that support radial loads, and we get bearings that support axial loads. Right, now radial loads, right? As I noted here, radial loads refers to loads that are perpendicular to the line of action of the shaft, right? And then axial loads would be loads that are parallel to the line of action of the shaft, right? So bearings being essentially a support for the shaft um, is able to be a support or be a reaction that supports either radial loads or axial loads or both, depending on the kind of bearing you are looking at. Right, so you get bearings that support either radial loads or axial loads, and then you get bearings that are able to support both axial loads and radial loads. Right. Sorry about that. This thing is acting up today. Right. So you get bearings that support both radial loads and axial loads, and you get bearings that only support radial loads and only support axial loads. Right. For the most part here, we'll be looking at the kind of bearings that are able to support both axial and radial loads. Right. Right. Now, regarding the kind of loads that we can expect, right? Of the loads that are radial or axial loads, right? We get two types of loads essentially, right? Or two main types of loads. We get static loads, right? We get static loads, and then we get what is this? Dynamic loads, right? For instance, if we look at a belt drive, right? If you look at a belt drive could either be transmitting torque or power or not transmitting torque, right? Meaning on a standstill, essentially, right? So a static load for a belt drive system, we would get if the pulley or if the belt drive is not transmitting any torque, right? Now, when the belt drive is not transmitting any torque, right, the load we get that is being induced or that the shaft is being subjected to would be a static load. Now, the static load of a belt drive system is known as installation tension, right? And installation tension is equal to, first, it is denoted as TO, which is equal to T1 plus T2, right? Now for this section, bearings, right? Anything that has to do with a belt drive, we will assume that it is not transmitting torque. Hence, the load that the shaft is being subjected to by the belt system will be the installation tension, right? That is aside from the weight of the pulley, right? Because there's also the weight of the pulley to consider, right? The weight of anything that has essentially been installed or been fitted onto the shaft, right? Now, as far as the weight will depend on the problem you're looking at, right? Sometimes they say that the weight of the particular mechanism is essentially negligible, hence you do not consider the weight. Sometimes they do give you the weight, or they give you the mass, right? Essentially telling you that the weight of this particular mechanism is of considerable weight, hence you have to consider it, right? Otherwise, just looking at static loads as well as dynamic loads. Regarding belt drives, we'll only be using or will only be looking at belt drives from the perspective of static loads because we always assume that the belt drive is not transmitting any torque. Right now, just for interest sake, this will cover more when we look at belt drives, right? But when the belt drive is transmitting torque, hence transmitting power, right? We then say that now the belt drive is transmitting torque, hence the load is no longer static but dynamic. And the dynamic load for a belt drive is known as effective tension. Right now, effective tension is denoted as TE, and TE is equal to T1 minus T2. Right. So this here is a dynamic load for a belt drive system, right? And that is denoted as, or that is known as the effective tension. Effective tension is denoted as T sub E, which is equal to T1 minus T2, right? And then if the belt drive is not transmitting torque, which we'll always assume for bearings, we instead use the installation tension. The installation tension is regarded as the static load for belt drives, and it is equal to T1 plus T2, right? Now, I'm assuming people did N1 up to N3, right? In N2 and N3 engineering science, we do cover belt drives, right? The reason why I'm saying that is because I'm assuming people are aware of what T1 is and what T2 is. Is that the right assumption to make here? Or must I explain what T1 and T2 is?
Can you please just refresh our memory, sir?
Right. Okay. Right. So this is how a typical belt belt drive system would look like. Right. So let's say an open belt drive system. Right. Because you get two types of belt drive systems. You have an open belt drive system as well as a crossed belt drive system, right? So a typical open belt drive system would look like this one, right? Where you have two pulleys, one being the driver, right? One pulley being the driver, say that's the driver, and then the other pulley being the driven pulley, right? And then for the pulleys or for power to be transmitted here, they then wrap the two pulleys with the same belt, right? Connect them to a motor, right? And then that's how they essentially transmit torque or transmit power through the belt, right? Now, the belt has two sides to it. There's this side and there's that side. Now, this side, right? This is the side where the belt experiences the most tension, right? And that side is known as the tight side, right? And the tight side is denoted as T1, right? And then you get the other side of the belt, right? There's the other side of the belt is essentially the slack side, and the slack side is denoted as T2, right? So the side of the belt that experiences the most tension or that experiences the most stress or is subjected to the most stress, right, is known as the tight side, and the tight side is denoted as T1, right? And then the other side is the slack side. Hence, I tried to show a bit of slack on this side, right, to show that this represents the slack side, and the slack side is denoted as T2. Are we clear?
Yes, sir.
Yes.
Right. Right. So that is any and all information you need to know regarding um, if you are looking at a problem where you have a shaft, right? The shaft is supported by bearings, and the shaft is fitted with a pulley, right? So the way we use the forces or the loads that the pulley is inducing or the belt drive is inducing on the shaft is by using this here, right? The static load of a belt drive, which is the installation tension. The installation tension is equal to T1 plus T2. So they would give you T1 and T2, right? Sometimes in the bearings you get a problem like in last year's exam, right? Was it last year's exam? I think it was last year's exam, right? Where they just gave you. Okay, I'll have to look for the paper because I don't remember what the question was, but it had to do with the pulley, right? It had to do with the pulley and the tension that you had to use was installation tension. But I'll look for the question paper, right? So we can do that question, right? But for now, just know that under bearings, right, the load being induced on the shaft the um, by the belt drive is essentially a static load, and that static load for a belt drive is known as installation tension, which is equal to T1 plus T2, right? And then, of course, if you're considering the weight of the pulley as well, then you would add the weight of the pulley, right? Um, as you know, regarding forces, right? Force is a vector quantity, right? So with vector quantities, we consider both magnitude and direction, right? So this year, it will depend on the direction of the belts, right? If the belts are pointing upwards, then you take the insulation tension as being positive, essentially, right? Because it will be pointing upwards, and forces going up, you take as being positive. Forces going down, you take as being negative, right? So if you're looking at a problem, and you have um, and the shaft is fitted with a belt drive, right? And the belt drive or the belts are such that the belt tensions are such that they're pointing upwards, then you take this, then you take the installation tension as being positive, and then if they're considering the weight you obviously take is being negative, right? So essentially, the force or the load acting, right, acting perpendicular to the line of action of the shaft will depend on the sum of the weight and the installation tension, right? If it is negative, it means that force is pointing downwards, right? If let me see, if this if the installation tension is such that it is overcoming the weight, then it means the sum of the weight and the installation tension will be positive. Hence, the force that is perpendicular to the line of action of the shaft will be pointing upwards. Right now, that is important to note, right? Because in a typical case where you have a shaft, it has bearings, it is fitted with a gear wheel as well as a belt drive, you would have to calculate the reactions at the supports, right? Hence, us saying that the bearings essentially act as supports. So when they want you to calculate the reactions at the supports, you essentially have to calculate the reactions at the bearings, which are what we take as supports here, right? Are we clear on forces or loads that the belt drive can induce onto the shaft?
Yes,
Hello.
sir.
All right. Right. Then we get a gear wheel, right? If you have a gear wheel fitted onto the shaft, right, we have to look at the forces that meshing gears are subjected to, right, while they are in mesh, right? There's three forces in particular. We'll talk about them just now, right? Now, depending on which of those forces is perpendicular to the line of action of the shaft, that is the one that you use, right, in applying conditions of equilibrium, right? Have you guys done beams? I assume you have if you've done N2 and N3.
Yes, sir, we did.
Maybe you know it as statics or you did.
Yes, that's true, sir.
Okay, right, right. So I'm guessing people understand what I mean by applying conditions of equilibrium, right? So in applying conditions of equilibrium, there's essentially two conditions, or two main conditions, because there's a lot, but there's two main ones, right? There's the sum of forces in one direction is equal to the sum of forces in the opposite direction. And then the other one is in terms of moments, right? The sum of clockwise moments about a point is equal to the sum of anti-clockwise moments about the same point, right? Mathematically, you could express them as sum of forces going up is equal to the sum of forces going down, right? So essentially, this one is the sum of forces in one direction is equal to the sum of forces in the opposite direction, right? You can express it like this mathematically. If you are asked, right, to state maybe two conditions of, equilibrium, instead of writing that long story, you could simply just use this here. This is correct. This here is a mathematical symbol called sigma, right? So this is sort of like shorthand for that long story I just said it, right? And then the second main condition of equilibrium is clockwise sum of clockwise moments is equal to the sum of anti-clockwise moments. Right? That is just a bit of revision. Right? So in science, if you are asked to state two conditions of equilibrium, you could simply just write this here. Right? If this is 2 marks, then this is 2 marks. If both are 2 marks, then this will be 2 marks, and this will be 2 marks. Right? Are we clear here?
Yes, sir.
Right. Now, in applying conditions of equilibrium, right, you obviously need forces that are um, parallel to each other, right, or parallel to the Cartesian plane, right? Now we've covered which forces to consider when looking at a belt drive, and then forces to consider when looking at a gear wheel, right? Are the forces that meshing gears, right, are subjected to when they are in mesh, right? So depending on the forces we're about to speak about, depending on which one is perpendicular to the line of action here, that is the one you use in applying conditions of equilibrium, right? Right, now let us look at those forces that meshing gears are subjected to, right? But now you should know that this here is the gear wheel and this here is the pinion, right? And because in a gear system, for the most part, you want a gear system where you'll be able to output the most torque from, right? And what actually influences torque is the radius. The bigger the radius, the bigger the torque that your gear system can output, right? Hence, in a gear system, right, when just looking at two gears in mesh, right, you would fit the input shaft onto the pinion and fit the output shaft onto the gear wheel, essentially, right? Now, forces that meshing gears are subjected to, right? First of all, for there to be any kind of motion, right? So essentially angular motion, right, for gears in mesh. For this, or for motion to be initiated here, you need to have a force being applied, and that force being applied is known as the tangential force, right? So first you get a tangential force. Tangential force is the force that is applied essentially for there to be any kind of motion, or for motion to be initiated, right, for meshing gears, right? So you get the tangential force, the tangential force because it acts tangent to the gears, right? Right. And then you get what we refer to as the radial force, right? Now, the radial force for gears in mesh, right? It's that force that essentially tries to take the gears that are in mesh apart, right? So the radial force for this one would be in that direction, and the radial force for this one would be in that direction. So this is Fr, right? So the radial force is essentially the force that tries to take the meshing gears apart, right? If you look at meshing gears, where they mesh, it's like something is trying to pull them apart, right? But because the radial force for each of the gears is the same, right? Essentially, this remains in dynamic equilibrium, right? Meaning that essentially, as much as this is trying to take this gear in that direction, and this is trying to take this gear in that direction, essentially the forces end up essentially pulling each other together, right? Hence, we have what we call dynamic equilibrium, right? So we have the tangential force, which is essentially the applied force in order for gears to start transmitting torque, right? And then we get these forces here, which is the radial force, right? The radial force for both gears is the same, right? Then once you have that, as you can see here, right, the two forces, right, so the radial force as well as the tangential force form somewhat of a right angle here, right? So connecting the two forces, or tangent to the two forces, is not tangent. The hypotenuse of the two forces is known as the normal force, right? So depending on which of these three forces, right, is perpendicular to this line of action, right, that is the force you would then use in calculating the reactions at the supports, right? So, of course, for hence I said you get bearings that are able to support both radial loads and axial loads, right? So for what is this? For calculating um, the reactions supporting the radial loads, so loads that are perpendicular to the line of action, right? You'd essentially be calculating the radial supports, right, at the bearings, right? Right. Any questions so far?
No, sir. So far, so good.
Do we understand this 20 degrees, where it comes from?
No, sir. Is it not always given?
So the 20 degrees is always given. Even if it's not given, we always assume that the envelope angle or pressure angle is 20 degrees, right? But I explained this on
Yes, the table
What
was at
is
14.5 and at 20.
exactly. Yeah. And the reason why,
okay?
remember the reason why I said we are going to be using the 20 degrees involute system is because in bearings, they only use the 20 degrees involute system.
Okay, sir.
Yes. So this will always be 20 degrees.
20
Right?
degrees.
So
Okay, sir.
that is essentially the profile of the gears in use here. Yeah?
Okay. Yes, sir.
All right. Right. Now, regarding formulas to calculate each of these forces, right? It's pretty straightforward. Seeing that the forces are able to follow the triangle law, right? Remember, with the triangle law states that if you have three forces, right, three forces that are concurrent and coplanar, right, you are able to represent the three forces, or three forces acting on an object. You are able to represent those three forces by the sides of a triangle, which essentially we have done here, right? And the triangle formed is a right angle triangle, right? Hence, we are able to use what is this, trig ratios in calculating any and all of these forces, right? Now, of course, in order to be able to calculate any of these forces, you must have at least one force, and that one force will be the tangential force, because the tangential force, right, as explained, is essentially the force that is applied to the gears or tangent to the gears in order for the gears to start transmitting any torque, right? Now, you have a pinion, right, a small gear, and you have a gear wheel, right? Now, as you know, torque is equal to force times R, right? Torque is equal to, the general formula for torque is force times R, right? Now, for gears, right, this F is the tangential force, right? This stands for the total force applied, and the total force applied for gears is known as the tangential force, right? So essentially, for both the pinion and gear wheel, this will always be the same, meaning that the only quantity that influences torque is what is the radius, right? Now for gears, we do not necessarily use the radius, right? We use half the PCD, right? So to get the torque being transmitted by the pinion is going to be equal to the tangential force times half the PCD of the pinion, right? And then to get the torque being transmitted by the gear wheel, we use the tangential force, multiply that by half the PCD of the gear wheel, right? Now from this formula, right, if you've been given this, right, because remember, you do not necessarily have to use both formulas. If you can get the tangential force from one of the formulas, depending on what you've been given. So say you are given the torque of the pinion, or the torque being transmitted by the pinion, and you also have the PCD of the pinion, then you can just use this to get the tangential force, right? But if you've been given the torque being transmitted by the gear wheel as well as its PCD, then you obviously use this one to get FT. Either way though, whichever formula you use, you will get the same tangential force, right? Because like I said, this tangential force is the same as that one. Radial force, the same as that. Normal force, the same as that, right? Are we clear here?
Yes.
Right. So once you get the tangential force from either of these formulas, right, then to get the radial as well as normal force, you simply use trig ratios, right? If, for instance, you look at this here, right, this angle is always 20 degrees. That is based on the profile, right, of the gear, right? So if you have this angle and you have the tangential force is adjacent to the angle we are using, right? So if you want to calculate the radial force, right, so you take into account that the radial force is essentially opposite the angle we're using, right? So because this is opposite the angle we're using, and the side that you would have by then, once you've calculated the tangential force, will be adjacent to the angle, right? So the trig ratio, which is convenient to use here, right, would be tan, right? Remember, tan is equal to tan, the angle we've been given, so tan 20 degrees, right? Tan will be equal to the side opposite the angle, which is the radial force, divided by the side adjacent to the angle, which is the tangential force, right? Which is where this comes from, right? And then, assuming that this you've already calculated, so to get this, you simply cross multiply. So Fr is equal to Ft, which is the tangential force, times tan 20 degrees, right? Which essentially you do the same thing this side, right? So whatever you get this side is essentially the same thing you get this side, right? But I did highlight both formulas because of the fact that the torques will be different. So the torque being transmitted by this one will be different from the torque transmitted by this one for obvious reasons, right? So again, depending on which information you've been given, if you've been given information of opinion, then you stick with this. If you've been given information of the gear wheel, then you essentially stick with that. Either way, though, from the second formula, right, to the last formula, right, we are essentially looking at more the same formulas, right? Right. So to get the radial force, this is what you use, and then to get the normal force, right? To get the normal force, right? Bearing in mind that, remember, this is what you have the tangential force, right? So if you have the tangential force, you are looking for the hypotenuse of this triangle, right? You have the angle, the side you have is adjacent to the angle, and the side you're looking for is essentially the hypotenuse. So to get the normal force using trig ratios, right, cos would be convenient to use, right? As you know, cos is equal to the side adjacent to the angle divided by the hypotenuse. The hypotenuse in this case is the normal force. And then solving for the normal force, right, the normal force will be equal to the tangential force divided by cos 20, right, which, as you can see, is the same thing, right, even for the gear wheel, right? So in a typical problem for bearings where you have a shaft and the shaft is fitted with a pulley and a gear wheel, right, and it of course has reactions at the bearings, right? If you haven't been given, right, if they haven't, if say they've indicated which of the three forces is perpendicular to the line of action of the shaft, but they haven't given you the magnitude of that force, right? Now you know which formulas to use to go about getting that force. Are we clear?
Yes, sir.
Right. Now, types of loads we've already discussed. Right, you get static loads as well as dynamic loads. Right, most of this theory you're going to have to read on your own, on your textbooks. Right. Right. Types of dynamic loads. So you get types of loads, static loads as well as dynamic loads, and then you get different types of dynamic loads. Right. So you have the basic dynamic load rating. Right. This you are going to read. It's not really that interesting. Right. But you can read basic dynamic load rating is denoted as CR, right? Now this just like the term stimulate. I mean the term suggests, right? Basic dynamic load rating. This you only use in calculating the essentially the lifespan of the bearing, right? And this you normally are given by the manufacturer. Hence, I don't really find that I don't really find it interesting, right? Now, they do sometimes ask you to calculate it, right? Either way, though, you only find it in one formula, right? Well, say two formulas, right? You'll understand why I say one formula, right? But essentially two, right? And both of which are to calculate the lifespan of the bearing, right? Bearing, right? Bearing, right? Bearing, right? Bearing, right? Bearing, right? Someone has their mic. Sesona, you have your mic on. Thank you. Right. Now, the one dynamic load I want us to speak about is this one here, right? The dynamic equivalent radial load, right? It is denoted as PR, right? That one is denoted as PR. So the dynamic equivalent radial load, right? It is denoted as PR, right? Now PR, they say is like a hypothetical um, constant load that the bearing is being subjected to, right? Right at the center of the bearing, right? The way I always try to explain it is by using working strength, right? Now you get working strength and you get ultimate strength, right? So the ultimate strength would be the load that a material is being subjected to, right? So I liken, or we can liken the dynamic equivalent radial load to working strength, because this essentially is the the constant load that a bearing is subjected to at its center, right? Depending on if the bearing only has radial loads being subjected to it, or both, what is this, or both radial loads and axial loads, right? So the X and Y, right? The reason why I'm likening this to working strength, right, is because remember, in calculating the factor of safety, right, the factor of safety, we account for both the ultimate strength and working strength, right? So this here will be the working strength of the bearing, right? Because we essentially add the radial load as well as axial load that the bearing is being subjected to, right? And then factor in each of the loads factor of safety, right? So X is essentially the factor of safety of radial loads, or we use X as the factor of safety for radial loads, and we use Y as essentially the factor of safety of axial loads, right? Now, PR, right, just like in this formula, is equal to this here, right? So the radial support, right? So FR stands for the radial support at each bearing, right? So FR stands for the radial support at each bearing, right? And FA stands for axial support, right, at each bearing, right? So I made an example of this one here, right? So I want us to consider this diagram. Say you have a shaft, right? The shaft is being subjected to a radial load of 20 kilonewtons and an axial load of 10 kilonewtons, right? That is what the shaft is being subjected to, right? Now, looking at what each of the supports, right? What each of the supports is essentially taking from each of these loads, right? Now, if you look at this scenario, right, the scenario is pretty straightforward. You have a force being, you have a shaft being subjected to a force. The force is such that it is equidistant to each of the bearing, meaning from here, the distance from here to this bearing is the same as the distance from here to this bearing. Because of that, this would make this shaft symmetrically loaded. Right? So symmetrical means that the load that is being applied on the shaft is at equidistant from um, both, what is this, bearings, right? So meaning that because this is symmetrical, you could simply, instead of taking moments, you could simply use sum of forces going up being equal to the sum of forces going down. So because this is symmetrically loaded, symmetrically loaded, meaning that the force being applied onto the shaft is at the exact same distance from either of the supports, right? So essentially, since this is at essentially half the distance of the shaft, and the shaft is essentially simply supported, that means that this bearing will support half of this load, and this bearing will support half of this load. By using this, sum of forces going up is equal to the sum of forces going down. Right, you simply say FR A plus FRB is equal to, so those are the supports of the bearing going up. Force going down is 20,000 newtons, right? Now, because this is symmetrically loaded, essentially FRA is equal to FRB. So you can simply say, call this 2FR, right, which is equal to 20. So to get FR, simply divide both sides by 2. Hence, the radial load at each bearing will be equal to 10 kilonewtons, right? So each of these bearings in this scenario, right, radially, right, will be supporting half the load that the half the radial load that the shaft is being subjected to, right? Similarly with the axial load, right? The shaft is being subjected to a 10 kilonewton radial load, right? Again, the beam is, or the shaft is symmetrically loaded. Hence, this will be taking half of this axial load, right? So what you substitute here is the radial load at each bearing as well as the axial load at each bearing. So you won't substitute 20 and 20 here, but instead, as we've worked out or as we established that for this scenario, FR is equal to 10 kilonewtons. So here you would substitute the 10 kilonewtons, and here you would substitute not the 10, but the 5 kilonewtons. And then the factors they would have to give you, right? So these are given, right? So the radial factors X and axial factors Y, you are always given. Any questions regarding this one?
Sorry, sir.
Yes.
Could you just repeat the part of substituting on FR on that equation?
Right. So you have to understand what this represents, right? FR. So FR represents the the reaction at each support, right? So as we established here, that the reaction at each support is what? 10 kilonewtons, right? For each bearing. So because the reaction at each support is 10 kilonewtons, then that is what you substitute here. This represents the reaction at each support, right? Similarly with the axial support, right? This represents the axial support at each bearing, right? So we established that each bearing will support 5 kilonewtons of the 10 kilonewtons that the shaft is being subjected to axially, right? So hence here, you wouldn't support, you wouldn't substitute the 10 kilonewtons because the 10 kilonewtons represents the load that the shaft is being subjected to. This here represents the reaction at the support, the axial reaction at the support, right? So each bearing, right, supports 5 kilonewtons of this 10. You have 5 here and you have 5 there. Hence here, you would substitute 5 kilonewtons. Are we clear now?
Yes,
Yes.
sir.
Thank you.
All right. Right. This, I think we've already talked about. Normally, this you are given by the manufacturer, even even in problems you will be looking at. Right. For the most part, they tell you CR or the basic dynamic load rating from the manufacturer's table is such and such. Right. But there are problems where they ask you to calculate this, which is not a problem because you only you only really calculate this in two formulas. Essentially one, but two, right? And those formulas are both based on the basic life rating, right? Now, the basic life rating of a bearing is essentially how we consider the lifespan of a bearing, right? So we look at the lifespan of a bearing from two perspectives. One of millions of revolutions, right? And the other one, which will be in hours, right? So this represents how long how long the bearing has been estimated it will run, right? So for millions of revolutions, it means that the bearing has been estimated to at least run for such and such millions of revolutions before it starts showing signs of fatigue, right? And then if you're looking at it from the perspective of hours, right, this represents the lifespan of the bearing. So we say essentially this is the number of hours that we estimate the bearing will last before it starts showing signs of fatigue, right? So this formula, right, the basic life rating in millions of revolutions is denoted as L sub 10, and this is what you use to calculate the L sub 10, or the basic life rating in millions of revolutions, right? You use the basic life rating here, right? CR, and then PR is the dynamic equivalent radial load, which we just spoke about. And then this exponent P, right? This exponent P, or this will depend, the exponent or the magnitude of this exponent P will depend on the kind of bearing you are looking at. So if they say that you are looking at a roller bearing, right, then this P will be equal to 10 over 3. And then if you are looking at a ball bearing, then this P, this exponent P, will be in magnitude equal to 3, right? Right. So hence, I've shown you here what this P is equal to. So for roller bearings, the exponent P is 10 over 3. And then for ball bearings, the exponent P is 3, right? So when substituting, right, the exponent P, substituting CR, substituting PR, whatever you get here will be in millions of revolutions. Right? Similarly with the basic life rating in hours, right, that is denoted as L10H or L sub 10H, right? And this is how you calculate it, right? It's 1 times 10 to the 6 over 60 times. Now this N stands for the rotational frequency of the shaft, right, in revs per minute. So you substitute this N in revs per minute. So you do not convert it to revs per second. You substitute it as it is in revs per minute, right? The conversion has already been factored into this formula, so we do not need to worry about that. This N, rotational frequency of the shaft, you substitute in revs per minute, right? Then times, essentially, the reason why I was saying you use this in one formula is because L10H, right? L10H, that is the basic life rating, of, or in hours, is essentially equal to 1 times 10 to the 6 divided by 60 times N times L10. All right, so this is why now L10 is equal to CR over PR to the exponent P. All right, so that is why I kept saying you essentially use this in one formula, but you use it in two as well, because there are two formulas to calculate the basic life rating. But this here, or taking into account that this is equal to that, right, is essentially almost like using it only in one formula. Do you get what I'm saying?
Yes.
Right. Okay, I've explained this. All right, now let's look at an exercise. Let us look at an exercise. Okay, so this I already did. So let's delete all of this. Okay. All right. Now let us look at an exercise, right? So in this exercise, you have a shaft, right? And the shaft is fitted with a gear wheel as well as a belt drive, right? Now, if you remember in the first diagram we looked at, right, the tensions of the belt were pointing upwards, right? In this case, the tensions are pointing downwards, right, along with the weight of the pulley, right? So they've given us the weight of the pulley. This W of the pulley, this W represents the weight of the pulley, right? Meaning that this has a considerable weight, hence we need to consider the weight of the pulley as well, right? Now, as you can see here, the what is this? The installation tension, right, is essentially perpendicular to the line of action of the shaft, as well as the weight of the shaft. I mean, the weight of the pulley is also perpendicular to the line of action, right? So since both the installation tension and the weight of the pulley are pointing downwards, right, you can simply just take that as one point load, right? So by saying the installation tension plus the weight of the pulley, right? So remember installation tension. Remember installation tension, TO is equal to T1 plus T2, right? So adding T1 plus T2, right? And then adding the weight of the pulley will give us the 3050 newtons, right? So essentially, the load that's um, that's the belt drive system is subjecting to the shaft is essentially 3050 newtons, right? So in calculating the reactions and supports A and B regarding the belt drive system, we are going to use the 3050 newtons, right? And then regarding which force to use, right, regarding the gear wheel, they've indicated that it's actually the normal force that is perpendicular to the line of action of the shaft, and they've given us the magnitude of the normal force, right? So essentially, we have everything we need to calculate the radial supports at the bearings, right? Now, from the diagram, we do not see any extra loads, right? So we can assume there are no extra loads here, right? Now, let's look at the statement for this problem. The gear has a normal force of 1,300 acting vertically upwards. Its mass is negligible. So the mass of the gear wheel is negligible. Hence, they haven't indicated the weight of the gear wheel. The belt drive force acts vertically downwards, and its weight is 600 newtons. right? That we've already covered. No axial loads. There we go. No axial loads are present on the roller bearings, right? So there are no axial loads. The rotational speed of the shaft is 580 revs per minute. The radial and axial load factors are x 0.0, 0.55, and y 1,8 respectively, right? So 5.1, calculate the reactions at the roller bearings A and B. Right, so they want us to calculate the radial supports at the bearings. Right. Now, essentially here, you just apply conditions of equilibrium. Right. So you take moments in calculating the both reactions, right? And then you prove your answers, or you test your answers by using the other condition of equilibrium. So sum of forces going up being equal to the sum of forces going down. All right. Now, for these kind of problems, always, right, whether or of regardless of whether or not they told you to do so, right, always test your answers, right? So always in calculating the radial supports at the bearings, you use moments. So you use moments to calculate the magnitude of the radial supports for this one, and the same for this one. Then once you've calculated the magnitude using moments, you test your answers using sum of forces going up is equal to the sum of forces going down. Are we clear here?
Yes, sir.
Right? So always calculate the magnitude of the support using moments, and then test your answers always, right? Test your answers using sum of forces going up being is equal to the sum of forces going down, right? So let us look at this exercise, right? First, we're going to calculate the reactions at the roller bearings A and B, right? Now, as I mentioned, you solve these kind of problems by looking at it from the perspective of beams. So the shaft you take as the beam, and then the bearings you take as supports, right? We only have radial loads here, so we are only going to calculate the radial supports at the reactions, right? By applying conditions of equilibrium. Sum of moments going clockwise is equal to the sum of moments going anti-clockwise, right? So first, let us calculate the magnitude of the radial supports at A, right? By taking moments above B, right? So this is 5.1, right? You take moments, about B, right? Sum of clockwise moments is equal to the sum of anti-clockwise moments, right? So now we look at the turning effect each of these forces has towards point B, since we are taking moments above B, right? Now reactions, right? This is very important, right? The reactions, you always assume they are pointing upwards, right? So the reactions, you always assume that they are pointing upwards, right? Because we always assume that since they are supporting the shaft, right, they are supporting the shafts, they're supporting the essentially the loads that the shaft is being subjected to, right? So we always assume that the supports at the bearings are pointing upwards, right? Now, our assumptions will either be proven right or will be proven wrong, right? So meaning that since we assume that the reactions are pointing upwards, right? If the magnitudes we get, right, or if the direction thereof are positive, then it means our initial assumptions were correct. But if it happens that when you calculate the magnitude of a reaction and the direction thereof is negative, then it means the initial assumption was wrong, and that in actual fact, the support at the bearing is actually pointing downwards. Are we clear here?
Yes.
Yes,
All
sir.
right. Right. So let's take moments about B. Now consider force. Now let's consider the turning effects that each of these forces has towards B. Right. So if we're taking moments about B, right, will A be going clockwise or anti-clockwise? So A will be taking this direction because remember we're assuming that this is going up. So because it's going up, right, for this to have a turning effect towards B, it will go in this direction. Now is that clockwise or anti-clockwise?
Clockwise.
So this one is clockwise. So we say this is clockwise, right? Then we have the normal force. It is also pointing upwards. We are taking moments about B. So is this? So this would be the turning effect that this has towards B. Now is that clockwise or anti-clockwise?
It's also clockwise.
Clockwise.
Right. So this
Clockwise.
is also clockwise. Yes. Right. And then we have the 3050 newtons. Right. It is pointing downwards. So the turning effect that this is going to have is in this direction. Now, would you say that that is clockwise or anti-clockwise?
It's anti-clockwise.
Clock-
It,
Clockwise.
oh, I clockwise.
Oh,
Clockwise.
beautiful. Right. So this one is clockwise as well. Right. So all of the forces, when taking moments about B, have a clockwise turning effect. Right. So we have zero anti-clockwise um, moments. Right. So you have the reaction at A times the distance from A to where we are taking moments. So the distance between A and B, which is 450. So A times 450, right? Plus the normal force, which is 1,300 times the distance between the normal force and where we are taking moments. So what is the distance between the normal force and B?
350.
So that will be 350. So you have the normal force, which is 1,200, times the distance between the normal force and B, which is 350 millimeters. And then we have the 3050 and the distance between, right, this force. So the distance between the belt drive and B is 200. So you multiply this by 200. All of this is equal to 0, right? So you will get 450A, right? And whatever we get here, we would have to transpose to that side because we are looking for A, right? So this is 1,300 times 350 plus 3050 times 200. So I am getting 1,065 times 10 to the 6, right? Now that would have to transpose. So when you transpose this, it will become negative 1,065 times 10 to the 6, right? And then because we want to calculate A, we then divide both sides by the 450. Right? Obviously that cancels and we get the magnitude as well as the direction of A. Right? So this divided by 450 gives us negative 2366,667 newtons. Right? Now as you can see here, we got a negative magnitude, right? Or we get a negative direction, right? Meaning that our initial assumption that this was pointing upwards, right, is wrong. It means since our answer is negative, it means that this is actually pointing downwards. Are we clear here?
Yes. Yes.
Right, so that means that this
Yes, sir.
is actually pointing downwards. So that is actually pointing downwards. Right. So now that you've calculated the reaction at A, we are now going to calculate the reaction at B by taking moments about A. Take moments about what is this about A? So we are now taking moments about A. Sum of clockwise moments is equal to the sum of anti-clockwise moments, right? So now we are taking moments about A. So we are now going to look at the turning effect that each of these forces has towards A, right? We have the normal force is going upwards, so it's going to have this turning effect towards A. Now, would you say this is clockwise or anti-clockwise?
It's
Anti-clockwise.
So this is anti-clockwise, right? And then we have the reaction at B. The reaction at B, we assume is pointing upwards, the same as we did with the reaction A, right? So assuming that this is pointing upwards, it's going to take this turning effect towards A. Now, would you say that this is clockwise or anti-clockwise?
Also
Anti-clockwise.
anti-clockwise.
Second?
Anti-clockwise.
Anti-clockwise.
Yes, anti-clockwise. So this is anti-clockwise, right? And then you have this one. Now the turning effect that this has towards A will be this one. Now is this clockwise or anti-clockwise?
Clockwise, sir.
That is
This one is clockwise. So we've accounted for any and all clockwise and anti-clockwise moments, right? We have just one clockwise turning effect, and then the others have, or the rest of the forces have an anti-clockwise turning effect. So going clockwise is the 3050. So you have the 3050. Multiply this by the perpendicular distance, right, from the belt drive to where we are taking moments. So what is this equal to?
650.
50.
So 650. So this is times 650. That's the only clockwise turning moments. Right, so that is the anti-clockwise. So you have the normal force. The normal force is 1,300. No. Okay. So this is 1,300 times the distance between the normal force, or the distance between the gear wheel and the reaction or the bearing A, which is 100. So 1.3 times 100 plus the reaction at B times the distance between B and A. The distance between B and A is 450. So B times 450. Right, so now you calculate. So you're obviously going to have 450B, right, plus the 130000 is equal to 3050 times 650, which is 1,9825 times 10 to the 6, right? Now you take the 130,000, take it that side, so that you are left with 450B this side. So yeah, 450B is equal to 1,9825 times 10 to the 6. Now this becomes negative 130000, right? And then to get B, you simply divide both sides by 450. Right, that cancels. And then to get B, right, B will be equal to minus 13000 divided by 450. So I am getting here 4116,667 newtons. Right? And then once you've calculated both the reactions using moments, you test your answers using sum of forces going up is equal to sum of forces going down. Right? Forces going up. Right? Forces going up, we have the normal force as well as the support at this bearing. Right? So remember this we calculated, right, and found out that this is actually pointing downwards. So the only upward force is the normal force as well as the support at bearing B. Right? The support at bearing B was positive, meaning that the upward assumption was actually correct. So forces going up is the normal force, which is 1,300 times the reaction at B, which is 4116,667, is equal to forces going down, which is this here, the 3050, and the reaction at the support A. Right? So we have this. So this plus the 3050. Right? Now both sides should be equal. You have 1,300 plus 4116,667. So this is equal to 5416,667 is equal to 2366,667 plus 3050, which is also 5416,667 newtons. Right, I forgot the newtons. So this is newtons as well. Right, and that will complete calculating the reactions at the supports. Right, so this would be the expected approach, right, in calculating 5.1. We good?
Yes, sir.
Right. Now let's look at the next question. 5.2 calculates the dynamic equivalent load for each bearing. Right. So that is essentially PR. Right. They are looking for PR, the dynamic equivalent. Now the dynamic equivalent radial load, right? They sometimes just say calculate the dynamic equivalent load, right? Because remember, you get bearings that are only subjected to axial loads. You get bearings that are only subjected to radial loads, and then you get bearings that are subjected to both radial and axial loads, right? Now, for this one, they did say we do not have axial loads, right? Even from the diagram, we could tell that we do not have radial loads, right? Right. So in calculating PR, right? In calculating PR, bearing in mind that the dynamic equivalent radial load for each bearing, right? We are going to have to calculate individually because each bearing has a different magnitude, right? So because of that, it means you are going to calculate the dynamic equivalent for bearing A and the dynamic equivalent for bearing B, right? Remember, this is not, or the shaft is not symmetrically loaded, right? Hence, the magnitude, right, of the reactions at the support is different. And because it's different, you have to calculate the dynamic equivalent for each bearing. Are we clear here?
Yes, sir.
Right. So calculating 5.2. So calculating the PR for each bearing, we'll first calculate for the for bearing A. Right, so this is equal to FR, the radial support at A, right, times its factor of safety X plus the axial support, right, at A times its factor of safety, right? So this will be equal to the support at A is equal to this one. So this will be, so that was the support at support A or reaction A times X. They gave us the value of X, it's 0.55. Right, so the value of X, right, the radial and axial load factors. So this is the radial, right, load factor, which is 0.55. So the value of X is 0.55. Now, as you know, there are no axial loads, right? So we leave the axial loads out. So 2366,667 times 0.55. So I am getting 1301,667 newtons, right? Right. And then to get the dynamic equivalent for bearing B, right? Now you've already shown how to use this formula, or you've already shown this formula, right? So essentially you are using the same formula, so no need to indicate the same formula again, right? You can just jump into substitutions because you already shown the formula. Right, so here for the second bearing, you can simply just substitute, right? You can simply substitute. This was the magnitude of the support at B, or at bearing B, right? This multiplied by the radial load factor, which is 0.55. So 4116,667 times 0.55 is 2264,167 newtons. Right, and that's how you would calculate the dynamic equivalent load, right, for each bearing. Right? Any questions?
No, sir.
Right. So now do you get what I meant by this representing the radial support at each bearing? Hello.
Yes, sir.
Right. Now next question. 5.3, the basic dynamic load rating. So the basic dynamic load rating is CR. Right. The basic dynamic load rating for A and B, if each bearing has to have an operating life of 13,500 hours, right? So we'll be using the formula to calculate the lifespan of a bearing from the perspective of hours, since that is what they've given us, right? In terms of hours, the basic life rating is denoted as, so that's 5.3, right? Yes. Is denoted as L10H, and L10H is equal to 1 times 10 to the 6 divided by 60 times the rotational frequency of the shaft in revs per minute times, so this is what you're calculating, CR for the A bearing. So this divided by the dynamic equivalent for bearing A to the exponent P, right? So now we look at what each of these quantities are equal to. Right? This we calculated, this we get from the statement. This here is 13,500 hours, and this will depend on the kind of bearings we are looking at. Right? The rotational speed of the shaft is this. So the speed is running at 580 revs per minute. Right. Now is this or there? Roller bearings, or they mentioned it here as well. Right. So these are roller bearings. Right. And the exponent P for roller bearings is 10/3. Right. So remember, for roller bearings, the exponent P is 10/3. For ball bearings, the exponent P is 3. Right. So we have 13,500 is equal to 1 times 10 to the 6 divided by 60 times N is 580 revs per minute, times we are looking for CR for bearing A divided by, now PR for bearing A was equal to this here. All right. So substituting that, right? And then the exponents. Remember, this is a roller bearing, so the exponent P is equal to 10/3. Right. Now from this point, right, you can use whatever mathematical method to calculate CRA. Right. You do not necessarily have to follow exactly what I'll be doing here to calculate CRA. Right. The Meccano essentially ends at this point. Right. After this, it's just simple mathematics. Right, so from here you have 13,500. So this is 1 times 10 to the 6 over 60 times 580. So that is equal to 28,7356, right? Times essentially the same thing. And so times this. Right. Now from this point, I'm going to divide both sides by the 28,7356. So 28,7356. So 28,7356. Obviously that cancels, right? So this side, right, you're only left with this, and you're left with this on this side. Right, so essentially this is what you're left with. So this I'm gonna put on the right hand side now. Right, is equal to, okay. Okay, maybe let me do this. Right, is equal to this here. Right, now to get rid of the parentheses, you simply multiply both sides by exponent 3/10. So you multiply this side by exponent 3/10. Obviously that cancels. So you rid this side of these parentheses, right? So this side you're left with CRA, right, divided by the 1301,667 is equal to this. Right. Right. Now all you do is you multiply both sides by this here. Right. So if you multiply this side by this, that's going to cancel this side. Right. So you multiply this on this side as well as on this side. So essentially, all you do is multiply both sides by this. So essentially, you will have this on that end, right? So CRA right, so essentially CRA will be equal to this, right? Will be equal to, let's do this instead, right? Take that there, right? So now you can calculate to get the value of CRA. So CRA will be equal to the 13,500 divided by the 28,7356. All of this to the exponent 3 over 10, right? Times the 1301,667, right? Which is 8242,784 newtons, right? So CR for bearing A is equal to this here. So now we calculate CR for bearing B, right? So again, you can be smart about this one as well, because as you know, we are going to use the same formula, right? So no reason for us, there's no reason for us to essentially jump through all these hoops. We already know that if we take this approach, right, it's going to bring us to this step here, right? So this side will remain the same because L10H is still 13,500, right? This is still equal to the 28,7356. The only thing that really changes here is what is the dynamic equivalent, right? So instead of doing all of this, because you've already done it, right? And essentially in calculating CR for bearing B, you take the very same approach, right? You can simply start your solution at this point, right? With this being different. Because remember this, right? This represents the dynamic equivalent, right? So this was the dynamic equivalent for bearing A. So meaning for bearing B, we are going to use the dynamic equivalent for bearing B here. Do you understand what I'm saying?
Yes, sir.
Right. So we simply say CRB is equal to 13,500 divided by the 28,7356 to the exponent 3 over 10 times, and then you use the dynamic equivalent for bearing B. So this is what you use. All right. So this is what you use. And now you simply calculate, and then you will get CR for bearing B. Right. So here I get 64,167. So here I get 14,337, say 8 newtons, because this it's actually 7996, right? So instead of, well, when rounding off to 3 decimal places, right, this will simply be 8, right? Hence I have just 8 here, right? Because remember, the final answers must definitely be rounded off to 3 decimal places, right? Now for accuracy, as you can see, sometimes I round off to 4 decimal places, right? But that is because I want my answers to be as accurate as possible. If you want your answers to be as accurate as possible, right? So during the calculation, you can round off to more than 3 decimal places. The final answer, though, must always be rounded off to 3 decimal places, Are we clear here?
Yes, sir.
Yes, sir.
Beautiful. Let's look at the next question. Oh, last question. So last question is, calculate the number of revolutions that each bearing can obtain before the first sign of fatigue occurs, right? So this is number of revolutions. So the lifespan of a bearing in number of revolutions is L10, right? So they want us to calculate L10, L10, which is equal to CR. So we're going to calculate L10 for both A and B. Now, bearing in mind that we would assume that the L10 or the lifespan of each bearing in millions of revolutions would be the same, right? But you need to calculate both anyway, right? So CRA divided by PRA to the exponent P, right? Now you substitute, right? In fact, this we've already done, so I can just copy from here. Okay, not really. Okay, not really. So CRA is equal to this. Let me copy that. It's divided by PRA. PRA is this. Right. So that's PR. So we are dividing here. And all of this is to the exponent 10 over 3. Right? Yes. 10 over 3. Right? And then let's see what we get. Remember, the answer you get here will already be in millions of revolutions. Right? So you have 8242,784 divided by 1301,667. All of this to the exponent 10 over 3. So this is 469,8. So it's 8004. So I'm just gonna write 8. All right. Now this answer is already in millions of revolutions, but instead of writing millions of revolutions, you can simply say times 10 to the 6, right, which mathematically represents millions revs, right? So this is how you would write down the units for essentially L10, right? So this is 469,8 millions of revolutions, which you represent by simply using times 10 to the 6 revs. Are we clear?
Yes, sir.
Right, and then doing the same thing for B. Now
Yes,
you
sir.
say L10B is equal to, right? So again, no need to punch the or use the formula again. You simply substitute now. So substituting CRB is this one, right? And then PRB is this one. Right, you're of course dividing here. All of this is to the exponent 10 over 3. Now let's see what you get here. So this is 14337, 8 divided by the 2264, 167. All to the exponent 10 over 3. So we're getting the same thing. 469, which is what you would expect anyway, 8 millions of revolutions, so times 10 to the 6 revs, right? Now you are expected to calculate both, right? It's a bit counterintuitive because you expect, right? Or maybe it's not counterintuitive because maybe if you get something different, then you know you did something wrong somewhere. Yeah, I guess so. Right, so you have to calculate both, and both have to be the same. We good?
Yes, sir.
Yes, sir.
All right, beautiful, beautiful. Yes, because this has gone to, yeah. So that is how you would attempt problems based on bearings. If you notice here, we've essentially covered everything on bearings regarding calculations. It's everything based on theory that you will do on your own. Right. I will highlight the kind of questions they like asking in the exam regarding theory on bearings. Right. But that we will talk about post 8 week test. Right. So in preparations for the exam. Right. I will highlight the questions they like to ask. In fact, you will see even from the past exam papers I sent you. Right. But we will discuss. Right. So we've covered everything we need to cover for the second assessment. Right. Now I know I said I will send the second assessment yesterday, but I couldn't. I was way too busy, even today. Right. But I will be sending it. Um, I will be sending it tomorrow, and then I will be expecting submission um, from Saturday to Sunday morning. So I will have time to do marking, because I will, this time around, I will do marking over the weekend, and I should be giving you back your marks on Monday. But again, that would depend on if you guys submit on time or not. But definitely Monday or Tuesday next week, I'll be giving you your marks. The test should be easy though, right? So you guys will have from tomorrow, right, to say Saturday to submit, right? Now, please make sure that there are no problems regarding um, the scanning of documents and submission, right? Some of you decided to do their own thing for test one, but I let it go for test one. For test two, I won't be letting it go, because I already laid down the standard for submission. It's pretty straightforward, right? You have your cover page first, right? And then next will be your answer script. And then everything must be in PDF format, only one file. Also, make sure when scanning that you scan in portrait, not landscape. Are we clear here?
Yes, sir.
Yes, sir.
Yes, sir.
All right, if there are no more questions, we are done here.
Okay, sir. Thank you, sir.
Is sir gonna send the recording on the group?
I will be uploading this onto my YouTube channel. Once I have, I will send you the link to that.
Okay.
Any more questions? Any more questions? All
No,
right.
sir.
No.
Okay, good. Enjoy the rest of your evening. Sayonara.
Thank you, sir. Bye.
Thank you. Bye.